Here is a question from Zach, asking how to stop the rain falling on something with an umbrella. It's boring. What if we tried to stop the rain with a laser that targets and vaporizes each drop before it can hit the ground from 10 feet away? The idea of stopping the rain with a laser sounds quite reasonable, but honestly, it's not very practical. First, let's consider how much energy the laser will require. The evaporation of 1 liter of water requires about 2.6 megajoules of energy, and in heavy rain, half an inch of precipitation can fall in an hour. Surprisingly, you can simply multiply these two numbers in a smart calculator, and the units will lead you to the answer in the form of power per unit area, which is exactly what we need. The calculator shows that we need 9 kilowatts per square meter that we want to protect with a laser. 9 kilowatts per square meter is almost 10 times more energy than the Earth's surface receives from the sun. And although it sounds like enormous energy, we must remember that water has an incredible ability to absorb energy. Heating water to boiling requires only about 10% of energy, while turning it from liquid to gas requires the remaining 90%. Ultimately, we are talking about filling the air with tons of hot steam. So, essentially, we are building something like an autoclave. It goes without saying that autoclaves are not the most popular places to live, but that's not all. Evaporating a droplet of water with a laser is more complicated than it seems. There are many studies on this topic, and the general essence is this. A lot of energy delivered quickly is needed to evaporate a droplet without breaking it into smaller droplets. This is what it looks like when a droplet is hit by a laser pulse. It can be noticed that I envy those who work with lasers and evaporate water. It can also be seen that the laser mainly splashes a droplet rather than evaporating it. This implies that complete evaporation of the droplet will likely require even more energy than we have already considered. The problem of aiming and targeting is also pressing. Theoretically, it could be solved, perhaps even without military equipment. High-speed cameras can triangulate the three-dimensional position of a baseball or soccer ball hundreds of times a second to help referees make decisions. A similar but more complex system could track falling raindrops. As for targeting, adaptive optics allows for quick and precise control of light beams. To cover an area of 1 square meter, about 500 direct light pulses per second would be needed. It is slow enough to avoid problems with relativity, but the device must be much more complex than just a laser pointer on a rotating base. It might seem easier to abandon targeting altogether and just shoot lasers in random directions. If you direct a laser beam in a random direction, how far will it go before it hits a droplet? It's quite simple. It's the same as asking how far you can see in the rain, and the answer is at least several hundred meters. So if you're not trying to protect an entire area by firing powerful lasers in random directions, it probably won't help. And honestly, if you are trying to protect an entire area by firing powerful lasers in random directions, it definitely won't help.